In splitting fatigue up into 2 weeks worth of work, we now turn our attention to thermoregulatory fatigue. So these are the ones that are outside the muscle. I'm talking about heat or cold impacting on what the body does and therefore causing a drop in power output. We're looking at the same bullet point this week because fatigue is multifactorial, meaning there are multiple causes. This week the focus will be on thermoregulatory fatigue rather than what occurs directly in the muscle. The overarching question then is, what is thermoregulatory fatigue? And hopefully the answer's in the name: thermo, temperature, regulatory, regulation. And what can we do to combat it? So it's really returning to some of the acute responses of the cardiovascular system that you're well aware of, namely sweating and redistribution of blood to the surface of the skin. The guiding questions quite simply here focus really on elevated body temperature, so hypothermia and then heat stroke. There is a little bit on hypothermia. That said, I haven't seen an exam question on hypo, which is low body temperature. A couple of little bullet points on what is dehydration, how to spot it, and then just linking back to what we know about sweating and sending some blood to the surface of the skin in regards to how that impacts on energy systems and bringing everything back to energy system into play. As we turn our attention now to thermoregulation, just a reminder that it's a fatigue mechanism that directly affects body temperature. And here's a picture of presumably an iron woman or a triathlete cooling herself down because she's probably become hypothermic with all the activity she's done. So hypothermia simply is an increase in body temperature. Okay, our core body temperature is about 37 degrees, but we can see that increase in exercise due to the muscle contraction, energy expenditure, the increase in blood flow to working muscles, and of course the external weather conditions will play a significant role in our body increasing its temperature. So obviously the body needs to manage this so that we don't cook ourselves, and that's called thermoregulation. So it's got to work out how to best get blood and oxygen to working muscles, but at the same time to cool the body down. Here's just a list of some more obvious perhaps aspects of contributing factors for hypothermia. So certainly just being physically active will contribute to elevated body temperature. Doing that in a warmer climate. Not adequately hydrating will increase the effects of hypothermia. You can talk about what you wear and your fitness level and a whole range of other factors. So there's some hopefully logic there to what happens to increase your body temperature. And you're more likely, as I said, to be talking about hypothermia in your exam than you are of heat stroke. But clearly here someone is still sweating for hypothermia. In terms of comparing hypothermia and heat stroke, it's really to do with the degrees of temperature that your body rises. So anything above 37 up to about 38 to 39 is hyperthermia, we've become hot. But if you're above 40 degrees, your core body temperature, that's heat stroke. And the big difference is that your body can no longer sweat, and that is that's dire. You do not want to have heat stroke. It can obviously lead to death. If your body can't then self-regulate its heat, thermoregulate through sweating and evaporation, you can be in dire consequences. And just a reminder again that body's mechanism to help cool itself down is to bring some of that blood to the surface of the skin or close to the skin via the capillaries and vasodilation of the arterioles there. And that has a consequence of taking blood away from the working muscles. So again, it's that balance the body must have of cooling the body down, but of also allowing it to do the exercise by getting the blood carrying the oxygen to the working muscles. Now, looking at dehydration, sweating and evaporation, all in line with hypothermia, let's think back to acute responses, and we've talked about what the circulatory system does in giving up some of that fluid from the blood plasma via the sweat glands, also in directing some of the blood to the skin, not to give up the fluid component, but just to get that red flushed face so that the blood passing closer to the outside environment can cool down. And here's an image of it. Looks like rugby players getting the big jet fans with some water spray to try and cool them down in the heat. And here's just a snapshot of some of the signs and symptoms of dehydration. Urine gets darker. There can be some headache, nausea. You obviously have a mild to severe thirst. And the sports scientists tell us that if we just drop 2% of our body weight, we can see a massive increase in perceived effort and a massive drop in performance or fatigue. That's why, particularly in hot circumstances, the pre-season games up in Darwin for the AFL, for example, rehydration is a significant recovery strategy for those players and teams. We'll look at that more closely in Unit 4 when we look at the different sports drinks, which we've already touched upon in our energy systems unit. Just to clarify, the cooling down aspects of the body, which start to go into the fatigue part of the course, but there's two aspects that lead to possible fatigue as cardiovascular responses to exercise. So the first is the sweat, where we lose fluid from the blood plasma via our sweat glands. As you can see with Rafa there dropping sweat off his nose and chin. That's different to the cooling mechanism that the body does by just redirecting blood to the skin. Okay, so there's two mechanisms there. We send some blood to the surface of the skin, and then we also give up fluid from blood, which cools us down via evaporation. So sweating via evaporation is far more effective, but both serve to help cool the body and bring our core temperature down. And so here's just an image of what's actually happening with the sweat glands. So the capillaries, still relatively close to the surface of the body, give up some of the fluid from the plasma through a sweat gland. When that forms water that water forms on your skin surface, hopefully with the breeze or a cooler atmosphere outside, we start to evaporate that and cool the body down. And in returning to that idea of what we can do to cool ourselves down once we become hypothermic, remember the two mechanisms from acute responses. This one that's listed in the heading is the redistribution of blood flow to the skin. So that's just getting the red face or the red muscles, if you like, the red skin. The blood's not giving up anything. It's just moving away from the core. It's moving away from the skeletal muscles. So in both cases, reducing aerobic efficiency. But what it's doing is cooling the body by having that blood closer to the outside environment than your inside body environment, and that helps to cool us down. Remembering also the second process was giving up fluid from the blood plasma via sweat to the skin, which hopefully can cool down via evaporation, assuming the outside environment allows that. So it's got to be cooler and there's got to be a breeze. Humidity and heat don't really work well with evaporation. And the explanation of how dehydration causes fatigue is similar to what we've already discussed with blood plasma volume dropping in our acute responses. As we lose some of that fluid, our total blood volume drops. What's still there is more viscous or thicker, which means the heart has to work harder to pump it around the body. And ultimately we are then impacting on our aerobic capacity, such that exercise must then draw increasingly on anaerobic pathways. And that's going to obviously hasten fatigue as we get the hydrogen ions that anaerobic glycolysis produce. Hypothermia can also be a cause of fatigue, but it's probably not one that we will talk about as anywhere near as much as hyperthermia. To remember the two, just remember that hypo has got an O, and so is the word low. So there's low body temperature, hypothermia. So the definition is 35 degrees or below for our core body temperature. And that's when your body starts to shiver involuntarily to generate heat. Now, similar kinds of impacts on performance as hypothermic in terms of dizziness and faintness and confusion, but not, as I said, as likely to be asked about this in your exam. Here's an interesting little bar graph for you looking at temperature and fatigue. Now, the temperature's on the horizontal axis and the vertical axis talks about time to exhaustion. So the bigger the blue bar, the longer the blue bar, the greater the resistance to fatigue or the greater your endurance capacity. So you can see here clearly that heat is the biggest killer for fatigue, the biggest precursor for fatigue. So 31 degrees here, your time to exhaustion looks like about under an hour. Conversely, 11 degrees seems to be the optimum temperature to do anything that is presumably endurance-based, and I have seen somewhere else that 12 degrees is the optimum running temperature for something like a marathon. Of interest, between the temperatures 4 and 21, there's a negligible difference, but not quite in between the two of them, but 11 degrees is the optimum. Just a little piece of trivia. I'll give you a hard copy of this in A3 again because I've done the work. I get the greatest value out of this mind map. But it's got fatigue front and center in grey
It branches off to the right with thermoregulation, which is mostly heat. It can be also the cold. And then to the left, we're looking at peripheral muscular fatigue and breaking that further down into fuel depletion and accumulation of metabolic byproducts. I really like mind maps. If you don't, that's fine. But I find a really good way to call back to my mind's eye when I'm in an exam condition or under assessment conditions.